The next cyclohexane we'll talk about is cyclohexane. And cyclohexane is the cyclohexane we will spend the most time on, not only because it's a very important, probably the most important cyclic system, but also because we will analyze its conformations in great detail. If cyclohexane was planar, then its angle would be 120 degrees. And that would distort, again, the sp3 hybridized carbons from their ideal conformation 190. However, cyclohexane is not planar, and through a series of concerted distortions from planarity, cyclohexane is able to achieve a conformation which is virtually strain-free and in which all carbons are tetrahedral. To draw this conformation out, we'll start with the first tetrahedral carbon. Here it is. And then we'll expand it to have each of the subsequent carbons be tetrahedral as well. So these are 2. And then the final carbon is here. This conformation is the so-called chair conformation. And at this point, I'm sure this will seem pretty daunting, and it is actually. And you should certainly practice this with models a lot, because just by looking at it drawn, it's difficult to perceive its three-dimensional structure. If we look at this, the reason, and this is the most stable conformation of cyclohexane. The reason for its stability can be seen if we look down these two bonds and present them in Newman projections. Now, we are allowed to do that. We can look at multiple bonds and present them simultaneously through a Newman projection as long as these bonds are parallel, so that our perspective remains unchanged. And so if we look at the left and the right circle, on the left we will see, in the front carbon, we will see the following conformation, which will then connect us to the right circle in a symmetric fashion. In the back, we will see that we are now in a staggered conformation, I mean not just any staggered conformation, but a gauche conformation, which positions the remainder of carbon-carbon chain at this 60-angle dihedral conformation. So this chair conformation is the most stable one, and in the future, when we start dealing with cyclohexane on a routine basis, we'll pretty much only deal with the chair conformation of cyclohexane. It's important that you learn to draw this very quickly, and to do that, the first thing we draw is one parallel line and some distance away from it another one, and they're both going from top left to the bottom right, but at a fairly steep angle. Then we're going to draw another set of lines pointing in the same direction, but not quite as steep, and then we're going to connect these this way. This is a little stretched out chair conformation, but basically you can do this yourself again. So it's basically a series of 3 sets of parallel lines, each set of these 2 lines. But the chair conformation is not the only conformation of cyclohexane. There is another way to arrange 6 carbons in a cycle and that have them all be tetrahedral. This is the other conformation of cyclohexane, which looks sort of like this, and it's pretty apparent why this is called the boat conformation. If we draw out the hydrogens in the boat conformation, making sure that everything is tetrahedral, we will start seeing important differences between these two forms of cyclohexane. The first thing that is apparent in the boat conformation is that these two hydrogens are relatively close to each other. That introduces some strain in the molecule, but the more important source of strain will be apparent when you draw the Newman projection along these two lines. And so on the front carbons, we will see something that looks like this. But in the back carbons, we will see exactly the same thing. So this now won't be gauche or even staggered for this matter. This will be the fully eclipsed conformation of cyclohexane. And this clearly introduces a lot of strain into into the system, and the boat conformation is the less stable conformation of cyclohexane. In fact, if we draw out the energy diagram for cyclohexane, the energy diagram looks sort of like this. I will first draw it and then explain what individual points are. So the most stable conformation, as I mentioned already, are cyclohexane chairs, and there are two mirror images of these chairs. So one of them looks like. The boat conformation, in fact, is a maximum, although very shallow maximum, and it's about 6.9 kilocalories per mole higher than the chair conformation. But the question is, what are these two remaining points? This one, which is 10 kilocalories per mole higher, is basically an envelope conformation. You remember the envelope from cyclopentane, but the envelope conformation of cyclohexane, where only one of the carbon atoms is distorted from planarity and the remaining 5 are still in the plane. Because of the torsional strain, this is very unfavorable. And this is about 10 kilocalories per mole worse. But a more interesting one is this conformation, which is basically like a boat which is twisted, and which is accordingly called the twist boat conformation, which is about 5.5 kilocalories per mole less stable than the chair conformation. The twist boat conformation, obviously there is this one and there is the mirror image of it, and this is a conformation which obviously is less stable than the chair. But in some specific cases, the cyclohexane actually does adapt twist boat conformation instead of the chair to release some other forms of strain. Now, if we continue looking at the cyclohexane and now just draw out the chair conformation in detail, what we will see is that there are certain hydrogens which are pointing straight up or straight down this conformation. There are 6 of them. And these are the so-called axial hydrogens. You can look at those as they're pointing along the axis of the cyclohexane ring, which is going this way. But the remaining 6 hydrogens are not as extreme. They sort of kind of look like a continuation of cyclohexane's own bonding patterns, just on hydrogen. And these are called the equatorial hydrogens. Because they're along this intersecting plane of cyclohexane, which is also called the equatorial plane. Okay? Now, in cyclohexane itself, these cannot be observed as individual hydrogens because they constantly interconvert between each other. And the process that interconverts them is the so-called chair flip, where we start with one chair, then we go through the boat conformation, and we get from here to here by lifting this part up, and then this boat converts into the other chair, so the mirror image of the first. If we keep track of one hydrogen, say this one here, what we will notice is that at some point this goes from axial to equatorial. And so the axial and equatorial average out over time. This process is very fast, so unobservable for us. And this is called the chair flip or the ring flip. But this difference between axial and equatorial becomes significant when we look at substituted cyclohexane. So if we have a methyl cyclohexane, then we can have this one with the axial methyl, or this one with the equatorial methyl. Let's look at the Newton projections and try to establish which one is more stable. So if we look at along these two lines now, what we'll see is two rings, and in the front we'll see something like this with hydrogens. In the back we'll see the familiar gauche conformation, but the metal group now will itself be in another gauche conformation with the rest of the carbon chain. Okay? Now if we look at the equatorial alternative, again we should see something like this. Metal group is now on the front carbon, but there's not much difference. And what we see in this case is the anti-conformation of the metal. And from that perspective, this appears to be more stable. There is, however, another effect that contributes to this, and that is maybe not so clear from here, but this hydrogen and this metal group actually interact. They turn out to be quite close to each other. If we draw the chair again and draw the fully expanded metal group, you'll see that these hydrogens in the metal group actually get quite close to the hydrogens on here. And this because these positions enable 1, 2, and 3, or 1, 2 prime and 3 prime. This will be the so-called 1,3 diaxial strain, which is a specific form of strain attributed pretty much exclusively to cyclic compounds, cyclohexane. And this strain again is relieved through the ring flip, which now distorts this metal group to the point that it no longer interacts with the crystal. Now, it seems pretty straightforward that the larger the substituent, the larger this effect. And so if we look at some general equilibrium where we have X substituent equatorial, or that X substituent, or that X substituent axial, various substituents will prefer they will all prefer equatorial. That goes without saying, but they will prefer equatorial, but different extents depending on their size. And so if you look at fluorine, it's a small atom, and so in kilocalories per mole, this difference in energy is 0.2. We move to chlorine, this is 0.5. We move to OH, this is 1.0. We move to CH3, this is the one we just talked about, 1.8. CH2, CH3 is 1.9. Isopropyl, so CH3 twice, is 2.1. T-butyl is actually very large, 5.4. And then if you look at cyano, for example, which is a linear substituent, so it points right away from the ring, it's a very small value of just 0.2. So here the size and the shape matter both, and this is an important effect. Now as we look at two groups on a cyclohexane, they would both prefer to be equatorial, right? And so if possible, they will do that. So if we have two metal groups and they're both axial, so this is the diaxial, they will destabilize each other. They will bump into each other, and they will quickly ring flip to exist exclusively in the diequatorial conformation, shown here. Now, but with trans cyclohexane, the two conformations are the same, right? Or the same in energy. So if this is axial and this is equatorial, the ring flip will switch them. So this will now be axial and this will be equatorial, but overall one axial, one equatorial doesn't make a difference in energy. And so while in case of the cis thing, this is clearly better, in the case of trans isomer, this is same. Okay? But now if substituents are different, again, if we have two substituents and they're different and they can both be equatorial, then they will do exactly that. So if we have isopropyl and methyl, both axial, the ring flip will get them to the diequatorial situation. But if they were if they are in a position that they cannot both be equatorial, then what will happen is that the bigger group will be equatorial and the smaller group will remain axial. If we look at the 1,2 isomer for change, so this is now has axial methyl and equatorial isopropyl. This conformation will be strongly favored versus the one which occurs after the ring flip, where the isopropyl is axial and methyl is equatorial. Okay? So this one is more stable and hence exists in larger quantities. The T-butyl group actually is so large that it's impossible to flip it, right? So this conformation is so much preferred that the other one virtually does not exist because the T-butyl group will never be axial. Because all the other groups are smaller than it, and so why would it ever be axial? The interesting kink to this argument comes from the study of molecules which have two T-butyl groups. Well, the only thing that is big enough as T-butyl group is another T-butyl group. And so what happens in those cases is that we take these two T-butyl groups, and so if this one is equatorial and this one is axial, ring flipping them will not help. But converting them to a twist boat structure, and I hope I'll be able to reproduce this. I'll just say that this is a twist boat, will allow both of them to be in a sort of semi-equatorial arrangement. And so in this is one of the cases where twist boat is the more stable one, even more stable than the chair conformation. Now, as the final part of this lecture, and this doesn't have much to do with cyclohexane, we'll just briefly discuss bicyclic molecules. The bicyclic molecule, as the name implies, have two or more rings together in the same molecule, and depending on the way these rings are joined, they can be fused, and this is the most common type, where they share a bond. Or they can be bridged, such as here, where they share more than two atoms. And the final arrangement is the so-called spiral, which is actually relatively rare, but here the systems share just one atom. Naming of these compounds is actually quite interesting. So if we look at something like this, we will name this compound as an alkane, but with some amendments. First, we will count the number of carbons. And so this has 10 carbons, and we will name it as a decane. Since it has 2 rings, we will name it as bicyclo. But since not all 10-atom systems with 2 rings are the same, we will introduce some nominators to describe the nature of these connections. So we look at these 2 connecting points, and they're connected by 3 routes. This one, and this one. What we'll do is simply count the number of rings, number of atoms along those routes. So 1, 2, 3, 4. This is the longest route, and so this is 4. The second one is the same, so this is 4. And along the third route, there is only 1 bond, so there are no atoms, so this is 0. So it should be 4, 4, 0 decane. Another example would be a bridge system, which is this, again, bicyclo. We count the number of carbons, and this is 7, so this is heptane. And now we go along the branches. This branch has 2 carbons. This branch has 2 carbons as well. And finally, this branch has 1 carbon. So this is a bicyclo 2,2,1 heptane. The only system I will talk about a little bit more, and this brings us back to cyclohexane, is decalene. Decalene is, as I mentioned, bicyclo 4,4,4-decane. This molecule can be cis or trans. If we think about it, the carbons here are trivalent, so there is 1 more hydrogen here, 1 more hydrogen here, and they can both point above the plane of cyclohexane ring, or they can point to the different side, like here. If we try to draw out the conformations of decalene, what we'll see in the case of cis-decalene is that if we have 2 hydrogens pointing to the top, the 2 carbons have to point to the bottom. So this one will point this way, and this one will point this way, and then to close the ring we will get something that looks like this. So this will be the cis-decalene. Now the cis-decalene, maybe it's not so apparent from this conformation, but it does suffer from 1,3-diaxial interactions here and an adjacent carbon. But if we look at the trans-decalene, this is the first part of it, point 1 to the top and 1 to the bottom, and the remainder of the second ring fits right in. And so this is the trans-decalene, where the carbons, which are bigger substituents, are now equatorial, and so this is a favorable arrangement, and trans-decalene is more stable than cis-decalene. But now be careful about it. Cis-decalene and trans-decalene is stereoisomers. They cannot convert into each other by ring flip. And if you want to make a model and try that, that would be a good idea. So they just exist as 2 separate systems, one of which is the trans system being more stable. So we will finish here, and the next time we will start talking for the first time about reactivity in organic molecules. So it'll be a little bit of a concept switch from this and the past series of lectures, which talks mostly about structure.